Welcome back to my channel. This is Buddhist in California. So today I'm going to talk in detail about this book on quantum field theory. I posted a short video about this book a while back. So now in this video we'll go into a bit more detail. So here's the book, Quantum Field Theory in a Nutshell by Anthony Zee. I hope you can see that. So this book was published 20 years ago. Anthony Zee is a well-known Chinese-American theoretical physicist, and he's well-known in quantum field theory and particle physics. So this book, it's a comprehensive textbook on quantum field theory. So it covers all the main ideas in quantum field theory, starting with what is a quantum field theory, how you go from quantum particle mechanics to quantum field theory. So he explains that, and then he, following a similar process that other people also follow, he lays out the well-known quantum field theories of spin half particle electron and spin 1 particle photon, and also spin 0 particle scalar particles. So the quantum field theories for all these particles are exhaustively defined and described, and how one makes calculations in these quantum field theories using Feynman diagrams. Feynman diagrams are the workhorses of quantum field theory. So you need to learn what Feynman diagrams are and how to use them to make calculations in any quantum field theory. So Zee describes how the problem is set up. You start with the Lagrangian and of the problem that you are interested in. Take for example scalar quantum electrodynamics. So you have a scalar field which has Coulomb charge on it, and this scalar field couples to an electromagnetic field. So that's where the name scalar quantum electrodynamics comes. And of course both the scalar field and the electromagnetic field are Lorentz invariant. So the scalar quantum electrodynamics is also Lorentz invariant, and that's where the full power of Feynman diagrams comes into play to solve this problem, to make actual calculations which then can be compared with the experimentally determined values. So how does one go about doing that? So one starts with the Lagrangian. Lagrangian basically describes both the scalar fields. It has one component that describes the scalar field, and the other component describes the electromagnetic or the Maxwell field and the interaction between the two. So there are three main components: individual description of each type of field, the scalar field, the Maxwell field, and the interaction between the two. So one sets up the Lagrangian, and then from the Lagrangian one sets up the path integral, because that's the crux of the problem. You need to set up the path integral, and then you need to figure out how to solve that path integral. Of course, no one has ever figured out how to solve a complete path integral, so the best you can do is to approximate, and that approximation is done with the help of Feynman diagrams. So you approximate the path integral order by order. The lowest order is called the tree level order, and then the next higher order is depending on the number of Feynman diagrams. So the second order has one Feynman loop, and the third order has two Feynman loops, and so on and so forth. So here, what exactly is the difference between a tree level diagram and a loop level diagram? In the tree level diagram, the quantum fluctuations are ignored, so you don't include the quantum fluctuations. You just have the interaction between the two fields and minus the quantum fluctuation. In the higher order diagrams, in one Feynman loop, second Feynman loop, third, and so on, you have quantum fluctuations which come into being because of Heisenberg's uncertainty principle, and by their very nature, there you need to include all domains of energy, which means the energy can go from 0 to infinity, and that's what makes the handling of Feynman diagrams so difficult. And that's where these various techniques that Zee describes, how to handle these Feynman diagrams. First, how to set up the problem, the Lagrangian, the path integral, the simplification of path integral in terms of Feynman diagrams, the meaning of Feynman diagrams, then the regularization, that's kind of a tongue twister of these Feynman diagrams, and then you actually solve the Feynman diagrams to obtain concrete numbers which can then be compared with experimentally measured values. So modern interpretation of quantum field theory includes two parts. One is what I just described, what's known as renormalization. So this whole process I described is known as renormalization. The word renormalization indicates that one is fully aware of the fact that the energy can go up to infinity, and which would make the theory to blow up. But by using all these techniques of Feynman diagrams and regularization and everything else, one tames these infinities and to obtain a finite value, because a physical theory of nature must give you finite numbers. If it produces infinities, then that's not describing nature. So the quantum field theory's modern interpretation requires renormalization, which is to obtain non-infinite finite values, and the other part, which is also equally important, which came a little bit later, is renormalization. So renormalized quantum field theory was, as I described in my earlier lectures, was in place by the end of 1940s, and renormalization group, which actually was put in place by late 60s, by 1970. So what renormalization group does, which is also talked about in this book in quite detail, it basically gives you a way to calculate how the values of the physically measured constants flow with energy. For example, in scalar quantum electrodynamics, you have a scalar field which has a Coulomb charge on it. So this Coulomb charge, which could be the charge of an electron, how does it flow or vary with energy? So this is this is a basic insight of modern physics, modern quantum field theory and particle physics, and also in condensed matter physics, because same ideas apply there also. In a field known as critical phenomena, is that the physically measured quantities actually depend on the energy at which the measurement takes place. So the charge of an electron is not a constant. Contrary to popular belief, it actually changes with the energy, and so is true for the mass of the electron. So I was talking about scalar quantum electrodynamics. So if you go from scalar to a full scalar quantum electrodynamics is not really a physical theory, because there is no elementary scalar which has a Coulomb charge on it. So let's talk about an actual physically relevant theory, quantum electrodynamics, which is a theory of electrons interacting with photons. So in this theory, one is faced with this problem, okay, what to do with the charge of an electron and mass of an electron, what happens to them as the energy goes from the room temperature all the way to Planck level and beyond. So this is what the renormalization group does. It gives you a very good calculation technique to find out how the charge changes, varies with the change of energy, of the energy scale, and same for mass. So Zee covers these ideas. So in the end, I would like to do an appraisal. This is a very good book. It's considered to be one of the best books of 21st century, but it's not the best book. So like I have done earlier lectures, so it's in the same class probably as the best books, but if you really want to understand quantum field theory, then you need to use other books also. So this could be a book that you can keep by your desk to delve into, but this is probably not the best book to learn quantum field theory, the techniques, the Feynman diagrams, the renormalization, the renormalization group, for that I would suggest Matthew Schwartz's book, which I have talked about earlier in my earlier lecture, and Peskin and Schroeder's book, which is also pretty good. So this is probably I think the best books it can serve is as a help book. So if you want to clarify some concepts that you have learned from these books and you want to get a fresh perspective, then yeah, keep this book handy. But I don't think it can be quite successful as a primary source of information. Like you're starting out from scratch, you have no idea what quantum field theory is, then this is probably not the best book. Okay, so with that I would like to finish my lecture. I hope this was informative and you found it both useful and entertaining. And if you have any questions, you can check out the link in the video below. Okay, thank you for your attention. Okay friends, so let me speak a few words about the location I'm sitting in. This is the famous campus of the Stanford University, the world famous university located here in Northern California. So this is 150-year-old university, and it's a private university, so it's quite expensive, but it's ranked consistently among the top 10 universities in the world. So, and it has produced several Nobel laureates in sciences, literature and other fields. And so behind me you can see the mural, which is the world famous mural on the campus of Stanford University. So if you ever seen a website of this university or a prospectus, this picture is always, you must have seen this picture. Yeah, it's in every main website of the campus or the prospectus of the campus, they always include this picture. Yeah, this is a world famous mural. It's from the New Testament, Sermon on the Mount. So Christ is giving his famous sermon on the Mount just before he was crucified. Yeah, so that's what